Hello, everyone. My name's Aidan Hotan, and I'm the ASCAP project scientist from CSIRO Space and Astronomy.
And I'm Vanessa Moss. I'm the head of ASCAP Science Operations, and we're here today to tell you about our Sintel project, applying collaborative intelligence to the next generation of telescope operations. So to get started, we have a very long history of running telescopes under the Australia Telescope National Facility as part of CSIRO. Our latest telescope, ASCAP, which you see behind us, is out in the Murchison of Western Australia. It's on the land of the Wadjuri Yamaji, and it is a incredibly complex instrument compared to what we've done before. So bringing together more dishes in an even more remote location requires us to think differently about how we operate these kinds of complex systems and what the role of the human expert is as we go towards the future. So like I said, we here in Australia, especially, we have this long history of pioneering techniques in radio astronomy dating back to as early as the Parkes Radio Telescope and the Apollo missions. So we've started from a place where the way we would control telescopes was quite analog and manual. It involved people sitting in front of machinery, looking at dials, plugging in, different equations to get things going. As computers rose, we had much more automated processes. So, what it looks like today is a lot less analog, a lot more digital, but we're still evolving what the role of the human is in terms of operating these kinds of telescopes. So, now we're looking, with ASCAP, we have this unique opportunity to really, I guess, leverage the expertise within CSIRO and also learn from where technology has gotten us over the last few decades to build a system that's much more focused on collaborative intelligence and working with intelligent systems. And so a lot of the work that we're doing with ASCAP is pathfinding towards the next generation of even bigger mega facilities. As we want to look further out into the universe, fainter, do much more things that are of ambitious scale, it requires bigger teams, more distributed teams, and much more complex systems than we used to have in the past. More telescopes, bigger telescopes, many more monitoring points. And so that's where our Sintel project is really trying to explore how we can take what we're learning with ASCAP, build Sintel systems, and benefit from this and inform, I guess, how observatories look into the future. So now I'm going to pass over to Aidan to tell you more about the specifics of our Sintel project.
Thanks, Vanessa. Yeah, so as you said, these new generation of telescopes are really designed to answer some of the biggest questions about the universe. But to do that, we need more and better data. So our ASCAP telescope was designed to be a large-scale survey instrument. It has special receiver technology that gives it a wide field of view, and it's designed to survey the sky in various different modes over multiple years of continuous operations. So we really needed to operate as efficiently and continuously as possible to make the most of the time. Now, machines are great at helping us with that because they're capable of watching the system 24/7 with fantastic vigilance. They will spot when things go wrong, provided we can tell the algorithm what to look for. The difficult thing is a telescope like ASCAP, especially a radio telescope, involves an awful lot of signal processing between the sky and the image or the data products that our scientists use to research the universe. That means that it can be very difficult to look at the end product and figure out, well, whether there's a problem, and if there is a problem, what caused it in the first place. There's a lot of steps between those two. Now, that's the sort of intuition and knowledge that humans develop over years and years of experience. It can be very difficult to encode that experience effectively into an algorithm. So we have two factors at play here, and both of these, we think, are ideal for a collaborative intelligence project. So when we talk about the scale of these new next generation mega facilities, exactly what do we mean? Well, in the case of ASCAP, we're talking about 500,000 monitoring points spread across multiple different linked subsystems. And that's a lot of data in itself, even though that's nothing to do with the actual astronomy data path itself. We're also operating the telescope in the real world. It's in what can be a complex, changing environment that's subject to external factors, like radio interference from satellites, thunderstorms, lightning discharges. All of these sorts of things can introduce new effects into the data, many of which we don't want and might have to try to remove later on. On top of all of that, we also don't know everything about the universe. We're building this telescope because we want to understand more. which means there's the potential to make new discoveries. And if we're not careful, we might end up removing a new discovery from the data because we mistakenly think it's interference. And that would be very bad. So here's an overall schematic diagram of the data path through ASCAP. We start right at the front end with these phased array feeds that give us the wide field of view. And when we talk about complexity, here's just a simple demonstration of what we mean. So this is what we call a domino receiver element. It contains low noise amplifiers at the very front that turn the radio signals from the sky into a voltage. Then it has filter cars that select the right part of the frequency band for us to study. Then it has analog to optical converters that turn the radio signal into an optical signal on a fiber that we can transmit back to the central building for processing. Now, just one of these things has a whole bunch of different components and monitoring points, and there's 188 of these in each telescope, and 36 telescopes that make up the entire array. Combined with that, we have our central processing facility, which has a whole lot of field programmable gate arrays, thousands and thousands of additional components, and at the very end, a supercomputer, which itself is a complex national facility scale system. So where does collaborative intelligence fit into all of this? Well, it's really at the heart of our vision for how we hope ASCAP will operate in future. We have a whole bunch of different subsystems that are all acting on or looking at or responding to different parts of the hardware. And all of these create information that we need to feed into some sort of central nexus. Now, there's so much information going into this that we need machine assistance, algorithms, AI, to tell us what's important. So we're going to be using anomaly detection and data cleaning methods to try and find interesting things in all of that data. The thing is, this will only work effectively if we have our expert humans in constant dialogue with that artificial intelligence network. We need to be able to let the machine inform us of when interesting things happen, but then help the machine understand what caused them and whether we should be worried about them. So at
So
this point,
following
I'll
on
hand
from
back
what
to
Aidan
Vanessa.
said, oh, sorry, yes. So following on from that, where we're at right now, so because of the complexity that Aidan described and showed, automation is very much a part of what we do with ASCAP. Automation is at the core of everything because we really want to make the best use of our human experts and expertise, and otherwise trust the systems. So what we have right now is, in terms of the automation side, we've been moving from a model where the assumption might have been a human operator sitting at the desk towards semi-automated operations where we could kind of program schedules, to the point we're at now with Sauron, where it's an autonomous decision-making scheduler that captures the system state and what state the telescope's in, the environment, the pool of observations, and it makes those decisions and informs us when we need to step in, or so it's not collaborative intelligence in the sense for this project, but it is a way that we are collaborating already with the system. And what we've seen since adopting this automated approach with Sauron is a big increase in our overall observing efficiency in a given day. And thanks to consolidation, which was required to make the automation work better, we've seen a much higher success rate. And so we're working towards our full survey efficiency by having this automation in mind, but also how we're going to collaborate with the long term. So in terms of thinking about the collaborative intelligence side and where we can use artificial intelligence systems, like Aidan hinted at, because the system is so complex, a human can't possibly keep track of all the monitoring points and all the data, or even just provide a very quick data quality assessment. So what we're starting on instead as part of this project is using ML and AI to do error detection, to tell us what's in the system, to find outliers, things we didn't necessarily predict. And as we go forward in this project, that's going to evolve into a whole kind of collaborative intelligence workflow where we design, okay, how does the system respond to these things? How do we work with it? How do we inform it of new things? And, just really go forward as making this as much of a Sintel workflow as possible in ASCAP. So I guess to wrap up, I will click the next slide and hand back to Aidan to say something about where we're going next.
Yeah, thanks, Vanessa. So this is really a very experimental approach. We have these new large-scale mega facilities, and there's lots of different ideas around the world about how they should be run. I think with ASCAP, we have the chance to do something really different here and leverage some of the emerging technologies that we've seen over the past few years. Um, we really have an opportunity to let machines and algorithms do what they do best, while at the same time preserving and building that human expertise and experience, and empowering it with the assistance of AI and ML. So I'm really excited about what we can achieve with this, and it's been great to see all of the other fantastic projects in the Syntel FSP, and we can't wait to get started.
Yeah, we're looking forward to the future. So thanks everyone for listening, and we're looking forward to your questions too.